My name is Amitesh and this is a walkthrough on a calculus optimization problem. If a at least 0 is a non-negative constant, how to find the point on the graph of y equals square root x plus a that is closest to the origin. And this is based on my lectures at Princeton University where I've received a university-wide faculty teaching award. I'm going to show you how to think about this problem very simply and intuitively. We're going to start off with the first step is just to visualize what's going on. It's always really good to visualize. So find the domain of the problem as well. Okay, this is always important with optimization problems. So if we look at our function y equals the square root of x plus a, what is the domain of this function? A is a non-negative number. Okay, you can imagine a is 5 or something. Okay, a is a non-negative number. The domain is when x plus a is non-negative, right? X plus a has to be non-negative, which is the same as saying that x is at least negative a. Now, if a is something like 5, that means x is at least negative 5, just to give you sort of a mental visualization. But we're looking at a domain of the problem of minus a infinity. Okay, that's the domain of our function, is as long as x is at least negative a, we're in our domain, and our function is going to look something like this, right? You're going to have negative a, and you're going to have a function that is square root x plus a, so it's the translation of square root x, a units to the left. Okay, so you can sort of draw it like this. You know, you can draw it like this. If you tilt your head to the right, you're going to get a parabola, or 1/2 of a parabola, and you can kind of see at 0, x is 0, you're going to get square root a. Okay, so that's going to be your point here. And you want to figure out what point is closest to the origin. So you kind of see visually that as you go beyond, non-negative values of x, you're going to get further and further from the origin. So you sort of imagine maybe some point like this, somewhere in between is going to be closest. So that's just a mental picture. It's not good to rely on them, but it's good to correspond them to the final solution so you see what's going on. And the answer is actually going to depend on a, and that's very crucial because if a is 0, we're just going to get y equals square root x, and in that case you're just going to get this graph where the closest point to the origin is just the origin itself. So it's not going to be some point in between. So it's going to be dependent on a. So we're going to have to think about that carefully as we go along in our problem. And if you're enjoying this tutorial so far, don't forget to smash that like button and subscribe. I really love helping as many people as possible. So many people study calculus all the time, and just digesting this, having someone at a board to walk you through it, with you. I love reading your comments and hearing your thoughts as well. So please don't forget to hit that like button and subscribe for tons of content. I've got a whole playlist on my lectures on calculus based on my lectures at Princeton University. So here what I'm going to do now is I'm going to keep going with this, and I'm going to actually set up the optimization problem, which we're going to do with our calculus. So what we're going to think about is, let's just draw a graph again. We want to minimize the distance to the origin. Okay, we think about what do we want to minimize. It's an optimization problem. It's our distance to the origin. So imagine you have a point here which is going to be x comma y, but y is equal to square root x plus a. So it's going to be x comma square root x plus a. That's our point. And what is our distance to our origin going to be? Okay, our distance to our origin is going to be the square root, because it's to the origin. It's the square root of the square of the x coordinate plus the square of the y coordinate. So it's going to be x squared plus square root of x plus a squared. Okay, and that's going to just equal to the square root of x squared plus x plus a. Okay, that's our function that we want to minimize. And an important trick with distance minimizing problems that you should always be aware of is minimizing the square root of something is the same as minimizing that thing. Okay, so if we want to minimize this distance, we may as well work with the square of that distance, which is just x squared plus x plus a, which is much easier to differentiate, which is our next step. We're going to have to differentiate to find where the critical points are and find the optimum value for our distance. Okay, so our minimizing function, what's our function? Let's call it g of x. Okay, so our g of x function is going to equal to x squared plus x plus a. Okay, this is the square of the distance. When is it minimized? And again, we always think about our domain. In optimization problems, always remember the domain of the function. So the domain of the function is basically minus a to infinity. Okay, that's our domain of our function. We try to differentiate g. We get g prime of x is going to equal to 2x plus 1. Now, at the beginning of the problem, I told you that it depends on a, right? Which point is closest to the origin depends on a. but the derivative doesn't seem to be. So just think about for a second, where the a dependence is coming in. Okay, that's just a mental sort of problem, sort of test for you to think about. So we have this derivative. When is it 0? Basically, that's when our distance is going to be minimized, right? So that's our thinking process, and there's a subtlety there. So our derivative is going to be 0 if we set our derivative g prime of x equals 0. That happens when 2x plus 1 is 0, or when x is equal to negative half. Okay, so that's our critical point. Okay, now with our critical point, I'm going to write it down over there. With our critical point, we know that when x is less than negative half, when x is less than negative half, our derivative is going to be negative. Okay, so when x is less than negative half, our derivative is going to be negative. You can plug in a value, for example, if you like, and just see what it is. So when x is less than negative half, it's going to be, g prime is going to be negative, so g is decreasing, our distance is going to decrease, and then when x is going to be greater than negative half, our derivative is going to be positive. Okay, so our distance is going to increase. So we have a minimum at negative half. And you can sort of visualize, x squared plus x plus a is going to be some sort of parabola. Okay, so I'm just sort of drawing it. You're going to have a minimum. Its derivative is negative, then derivative is positive. Now, the key point here, and why I said the dependence on a is crucial, and my answer to my test to you is that you have to work on the domain minus a infinity, and you can't have extrema at endpoints. Okay, you don't want to just check the critical points, you want to check the endpoints, and negative half may not be in this interval altogether. Okay, so we're going to actually visualize this right now. Okay, so if negative half is in, negative half is in the interval negative a infinity, okay, if it's in that interval, then it's true that our minimum is going to be at negative half, at x equals negative half, right? That's just by what we just saw. It decreases and then increases. Okay, so then our minimum is going to be at x equals negative half. So our minimum is going to be at negative half, comma, what is our graph of our function? Square root minus half plus a. So comma, square root, you plug in x equals negative half into your y value, you get square root negative half plus a. So that depends on a, that's going to be our minimum. Now what if minus half is not inside that interval? Okay, so minus half is not in the interval negative a infinity. In that situation, if it's not in negative a infinity, then our minimum is not going to be at negative half. But remember that g prime is always positive when x is greater than negative half. So in that situation, you're going to have negative half, you're going to have negative a, you're going to have 0, and your domain is going to be like this, and g prime is always going to be greater than 0. So you sort of see that your distance always going to increase. So the minimum distance is just at negative a, x equals negative a, and that's just the example I gave you when a was 0 and it was just at the origin basically. So then our minimum is going to be at, I'm going to write this as follows, going to be at just when x is equal to negative a. So you're going to have negative a, comma, your y value when x is negative a is 0. So you're going to have negative a comma 0. So that's pretty cool so far, right? And let's just visualize it just briefly. So I always find it helpful just to visualize these problems so we can think about the first case is when your minus half is in negative a infinity. So a is very much greater than half. Let's visualize that, okay? So when a is very much greater than half, then you have something this, or negative a is very much less than negative half, then you sort of see that your closest distance in this sort of example should be somewhere here. It should be somewhere here. It's going to be when x is negative half. That's where your closest distance is going to be. Okay, it's going to decrease, going to get here, and then it's going to increase. Okay, your distance to the origin. On the other hand, so this is when basically you could say negative half is greater than or equal to negative a. On the other hand, when negative half is going to be less than negative a, you're going to have the following situation. Imagine that your a is very close to 0. You're going to have some situation like this, and in this situation, you can kind of see that your distance keeps getting larger after this point, right? It keeps getting larger and larger. So this is when negative half may be beyond the interval, and then you're going to have, this is going to be at negative a. So you're just going to have negative a there. So that's just a prototype to visualize. It all depends on a. I've got 2 fun videos for you, 2 graphing tutorials. I've got calculus across all topics and levels on my channel. It'll really solidify these concepts in this video. The first one is how to graph y equals x plus 1 over x. And there's a secret oblique asymptote there. So if oblique asymptotes are kind of sketchy for you, and just graphing in general, it's a very fun example. It's going to pop on the screen. You're going to love that video. And another complicated graphing problem, this requires so many tricks. It requires L'Hopital's rule for limits, concavities, second derivatives, first derivatives, limits at endpoints. It's a whole mass of everything in one go. You're going to love it. It involves a logarithm. Check that video out. It's graphing x times log x. You're going to love that video. Wish you an amazing day, and I'm super excited to catch you in either of these 2 videos.